Okay, I believe this is going to be the last video I do for this unit, because looking back on it after finishing calculus is actually a pretty easy unit, short unit. And this last one, I'm going to talk about differentiability, which, is basically kind of like continuity, but it's a little different because what differentiability basically means is that the derivative of a certain line will exist at a certain point. It doesn't always. So we learned that differentiability depends on something being locally linear. And locally linear basically means that if you look really, really, really close in, it would look like a straight line, aka it doesn't bounce randomly. An example would be something that looks like this. That's locally linear because it doesn't do this, which is like this right here. If you looked really, 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 really microscopically close, it wouldn't be straight. So if this right here is c, then this function, let's call it f of x, is not differentiable when when x equals c. So that's what locally linear means, and it needs to be locally linear for this to be differentiable. You should be able to draw a smooth progression of tangent lines to the left and right of a point on the curve, which just basically means that it's continuous and it's smooth. And then the last one is that the slope of the tangent line must exist, and this is important. Right here, I'm going to draw two graphs. One of them is going to look like that. And I'll show you these in a second, because I think the glare is going to make this impossible for you to see. One's going to look like that. These are both really similar. Actually, these are both really similar. But the difference is that at these points, there's a major difference, and that is that the tangent line for this one is a horizontal line that basically is y equals whatever this value is, aka it's just a horizontal line. It exists, the slope is just 0. But right here, we have a vertical line, and that means that the slope here is undefined, and if the slope here is undefined, then it's not differentiable at this point. So as long as it doesn't follow those, as long as it follows those three rules, it should be differentiable. Going back, the smooth progression means that it doesn't have a jump, or it doesn't have like a point of discontinuity, aka a hole. And as long as it has these things, then you should be able to call it differentiable. Now, you may see problems that are similar to the continuity problems. I don't have an example in front of me, so I can't really show you, except that it will say what are the values of a and b that will make something differentiable. And to do this, it's really not as hard as it sounds. All you gotta do is do the same thing, make sure it's continuous, doing the limit thing that we did at the beginning of this unit by doing the limit from the left equals the limit from the right, which equals that value. And then you have to do the limits again, but for the derivative, because the derivative has to exist at all points. It's a lot of work. You can do it. So let me just write this for you really quickly. You would have limit as x approaches, we'll just call it c, from the left of f of x equals limit as x approaches c from the right, f of x, which equals f of c. And you'll do this and you'll get one of the functions, but then you have to do this again to make sure these are differentiable, and do c from the left of x prime, or f prime of x. Same for the one on the right, and the same for this. And then you do a similar process, and that's how you would find what points or what values of a and b make it differentiable in a piecewise function.